Hello, in this video I would like to show you this. This is my current project, and this is a digital LED VU meter. So if you don't know what a VU meter is, it actually measures sound intensity and kind of displays that. And in this case, it's going to be done with a series of LEDs. So actually currently this isn't working, and I'll show you what it's doing right now. But I thought today in this video I would discuss the circuit, just an overview of the circuit, and some modifications I think I need to make. And hopefully, if it's all working, then in the next video I'll show you a proper demonstration. This is a kind of a neat project, I think, because it uses several op amps, and so I've been kind of learning about op amps, tinkering with them, and so if that's you, this is kind of a cool project that you could try. The idea of this project came from a few things that I've seen online, including YouTube and Instructables. And basically, it has two parts. So this top part here, which helps support the microphone, and then this part down here, which is what runs the LEDs. I tend to power through this screw terminal. I just stuck on some wires for now. And this is connected to this on-off switch. And then you'll notice there's a jumper here. There's one over here too, a black one. So there are two pins under here. Okay, these red pins here. So the bottom one is connected to the switch and also to the lower part of this board. So here down. And then the top pin is connected to the top part here. And the purpose of that is actually if I wanted to use this LED setup for something else, a different kind of signal, not just from the microphone, then that would allow me to sort of power the bottom without having to power the top. This jumper here there's three pins here. These two blue ones, this one in the middle is connected to this blue wire, which connects to these inputs, which I'll talk about in a second. And then this one here is connected to the output of the top here. This last one here, it's black. That's a ground pin. So if you're going to connect something external to this board, usually you need to connect the ground as well. So that's what that is. You might want to see the mess of the wiring, but that's sort of what I ended up with for the board. Okay. So let me talk about this op amp here. So this is the LM358. It is a dual op amp, meaning there's one op amp on one side and one on another. So if you know about op amps, you would recognize this triangle symbol. There's a minus and a plus. This is the inverting input and the non-inverting input, right? And so depending on what these are doing and the setup of this, then there's an output. Okay, here's the ground pin, so pin 4, and here is pin 8. So on here, this is, you can see a notch here, and that notch is right here. And then here are the 4 pins with ground on this side, and here are 4 pins, right, pins 5 to 8 with VCC here. So the VCC and the ground are what power the pin, or sorry, power the IC itself. And so then this circuit here is based largely off of this circuit here. And this comes from an Instructable. The title is Mini Decibels, a simple volume meter with an electric microphone, and there's sort of more to it, but I think if you search this, you'll find it. It's by Mark Moran. That's how it's written in Instructables. His name, I suppose, his name. And so then most of this circuit is actually based off of his diagram here. He does go on to connect to something else, but I'm going to use a different setup here with the LEDs. So basically, this circuit here is starting with this V plus here. So that would be my VCC, which I intend to run this project off of 5 volts. But that's connected to a resistor. This is 2K2, it says, so 2,200 ohms. And that's connected to a microphone, which is connected to ground. Okay, so here's the resistor and here's the microphone. And the connections are on the bottom. And so when sound hits the microphone, causes little fluctuations in the voltage at this point here. Okay, so if this is 5 volts and this is going to be something less than that, I don't know, like let's say 3 volts. I'm not exactly sure sort of where this would be, but let's say it's 3 volts. And then with the microphone, it would cause little fluctuations up and down from that 3 volts. And what we want is not the 3 volts, but those little fluctuations. So this capacitor is 10 microfarad, and so that blocks the 3 volts, but would allow the passage of the AC signal, those little fluctuations. That goes through a 1000 ohm resistor, and then that's connected here to the inverting input of our op amp, right? So one side of our chip. And then if you go back to this diagram here, that would be pin 2. Okay, pin 2. The other input, the non-inverting input, is connected to a voltage divider. So here V plus, and then there's a resistor here, it's 10,000 ohms, and another one here, 10,000 ohms, and then to ground. And there's a connection in between to the non-inverting input. And so I just like to take a second to talk about voltage dividers because it's a very, common concept. So you probably, if you're watching this video, probably know about it, but if you don't, then you really don't know what's going on in this project. So just briefly, if I can quickly talk about voltage divider with resistors. If you have a voltage, an input voltage, so V in for input, and in my case it's going to be 5 volts, but it could be whatever voltage in general, and then that's going to be connected to a resistor, which is then connected to another resistor, and that's connected to ground, or in this case 0 volts. Okay, and so then if you connect to the intersection of those, then this voltage here is going to be less than that. Okay, V. And if I name these resistors R1 for resistor 1 and R2 for resistor 2, then depending on the values of these, you can manipulate sort of what voltage you see here. So there's actually a formula for this. This voltage, or output voltage, would equal our V in, so the input voltage for the whole circuit, and that's multiplied by a ratio. And that ratio is everything after our output voltage, so all of the resistance all the way to ground. So in this case, it's only one. It's our second resistor, R2, divided by the resistance in the whole circuit from our V in all the way to ground. So that would be R1, and because these are in series, it's R1 plus R2. Okay, and that would be our, let's call this out, V out. And so that's our formula. So you can imagine if these were the same, let's say, I don't know, 10 ohms, for example, then our formula would be V in, which we're saying is 5 volts, okay, multiplied by R2, which is 10, divided by this, the sum of the voltages would be 10 plus 10, which is 20. Okay, and so if these are the same, you could imagine that this voltage here would be half, in our voltage divider, would be half of our V in, so that would be 2.5 volts. Well, 10 divided by 20 is half. Half times 5 is 2.5 volts, right? Halfway in between. And this kind of makes sense, right? If this voltage, if you increase this relative to that, make this really big, then R1 over R2, one number divided by itself is 1, but here we're adding something that's maybe very small, right? As R2 gets really, really big and let's say R1 gets really, really small, you could almost ignore this. It would be R2 over R2, which equal 1. V in times 1 would be V in again, right? So essentially what I'm trying to say is as R2 gets bigger, this gets bigger, right? Or closer to this. If I make this bigger, so R2 over R2, so R2 divided by R1 plus R2, if this gets bigger and this would therefore get bigger, then our fraction value would get smaller. So V in times a smaller fraction would give us a lower V out. So essentially what I'm saying is if R2 gets bigger, this gets smaller. Or if R1 gets bigger, this gets smaller. If R2 gets bigger, this gets bigger. Okay, and so that's sort of how voltage dividers work. Anyways, So with that in mind, then here this is 10,000 ohms, this is 10,000 ohms. So this input here is going to be half of that. So in our case, 2.5 volts. On the output here of our, that would be this pin here, pin 1. On the output, there is a feedback resistor back to the inverting input. So that's 1,000 ohms. So really this setup is a inverting amplifier. And if this is 1,000 ohms and this is 100,000 ohms and this is 1,000 ohms, so 100 divided by 1. So this setup is going to amplify by about 100 times. Okay, so these tiny little fluctuations are going to be amplified by about 100 times. This part of the circuit is sort of over here. If you want to look it up, Mark Moran calls this sort of an envelope follower, and in his instructable, he kind of directs you where he got this from. So if you want to look that up, please go ahead. But what we have here is an envelope follower. So what that does is it tries to sort of hold on to the peaks of the signal coming into it. And so that has another capacitor here on the output of this side, and that's 1 microfarad. And then there's a 10,000 ohm resistor going to the inverting input of this side. Okay, and then the non-inverting input connected to ground. And then on the output, there are 2 diodes. These are Schottky diodes. And so on our project here, it looks very dark. On our project here, that would be this component and this component. Okay, this is our 1 microfarad capacitor. This one here. This resistor is right there. Okay. There's also a 22K, so 22,000 ohm resistor here, a feedback resistor. Okay, so if this is 22,000 and this is 10,000, this actually would amplify by about 2.2 times. Okay, amplifying this signal. Okay, so that's sort of amplifying our tiny little fluctuations from the microphone, reacting to the intensity of the sound, and then we are amplifying it and then kind of holding on to those peaks. There is a capacitor here. This is 10 microfarad. That's this one here. And oh, I missed this. So there's a resistor here. That's right there. And then this is 10,000 ohms. When I had this circuit on a breadboard, I found it held onto the peaks a little bit too long. So actually, I reduced this by quite a bit. There's 2 resistors here. They're actually in parallel. And so then it's actually more like 150 and 150 in parallel. It's more like 75 ohms. Like way different. But I don't know, for whatever reason, maybe because what he has connected very different than what I have connected, but I reduced that by quite a bit. Anyways, that's the top part of this circuit. And then the bottom part has these 2 components. Okay, they are both an LM324, or I guess this version is specifically LM324N. So these are quad op amps. So in each chip, in each of these, there are 4 op amps. So almost like 1 in each corner. There is a VCC, so that would be powered by 5 volts, and this is, they call it VCC minus, but that would be our ground. So those are in here, VCC and ground, VCC and ground. And you'll notice this blue wire here is all connected, and so the signal here connects to all 8, okay, of our non-inverting inputs. So 3 and 5, pin 3 and pin 5, pin 12 and pin 10, they all have the same signal on both chips from this middle pin up here. Okay. And then the rest of it, you'll notice there are some potentiometers here and another one here, and then a row of resistors across the top. So that is this. And this was inspired by a YouTube video by Igor Brichkov. He was making some some like audio cassette player, but he was making a VU meter, and so that's sort of the inspiration for this project. So he used this resistor ladder to get different voltages across. So it's like one big, huge voltage divider with tapping off on these yellow wires at different places. So on here, these are the resistors that I have across the top. So there's a 10,000 ohm and a 2.2K, and those are these two right here. Okay. And then it connects to a potentiometer, and then another one, and then back up to the top here. Okay, and so on and so forth. These potentiometers, if I had, this is 10,000 ohms, and same with this. If I had a 20,000 ohms potentiometer, I would have used that, but this is what I had on hand. This one is just 1,000. And so then you can imagine for our voltage divider, right, our V in, again, is going to be 5 volts, and then the ratio is going to be R2, which is essentially since everything's in series, all of these added together divided by the resistance of the whole circuit. Okay, so on this end, this yellow wire goes to the inverting input. Right here, this voltage on this input is going to be much higher than the voltages on this end. This one is very close, so my V in is going to be 5 volts, but my R2 is really just this potentiometer, and then my R1 plus R2 is going to be everything. You can see that this voltage here will be quite small. And then the output of each op amp here, going across, is connected to a resistor. Each one of these is 100 ohms, just to kind of limit the current that goes to each LED. Right, so then depending on what this signal is coming in from this blue, each op amp is sort of comparing to its threshold tapped off yellow. And so if this signal is a higher voltage than this one, then this output will be high, and then this LED will turn on. If it's higher than this one, then this one will turn on. But if it's not higher than this one, and of course all the rest will not turn on, right? And so then that's how the VU meter works. Depending on the amplitude of that voltage, it will turn on or off a number of LEDs. Okay, at least that's the point. So I used the numbers that Igor has as sort of a starting point. And then if I go to the computer for a second here, let me just actually so if I go to the computer here, I used the numbers that Igor has as sort of a starting point, but then I kind of plug these into Excel to kind of to play with it and see what values did I actually want. So like I said, the first two resistors are 10,000 ohms and 2,200 ohms. And so that's sort of this cell here, B2. This yellow one is supposed to represent the two potentiometers. So it can go from very low to up to about 20,000 ohms. And so that allows me to play with it and then change to see what the output voltage would be, or sort of our inverting input voltage, right? And so then as you go through this resistor ladder, there are different voltages, or sorry, different resistor values going down here. Okay, and then this one here represents that 1,000 ohm potentiometer, again, which I can twist and vary and change the resistance, which will affect the voltage. This column here, sum above, so from that first yellow wire on the right there, all of the resistors above that, so basically this one and this one, is summed right here. And then sum below is everything from that point and lower. Okay, so that's what that is. And so then that goes the same through all of these rows here. Our input voltage is 5 volts. And then here, this is our voltage divider equation. So E2 is our 5 volts, and then D3 here is, from our formula before, that would be equivalent to our R2, right? The resistor values from this point back down to ground. And then C1 plus C3 is both of these together, the resistance of our whole circuit. Okay? So these would be the threshold voltages, at least theoretically, assuming that these are the potentiometer values. And you'll notice here I tried to graph this here. So we have LED number. Those are these numbers here. And I have 8 LEDs. So this is the threshold for the first one, the second one, the third one. And you'll see it's not linear. It's actually sort of a curve, because our hearing for sound, human ear, human brain, the hearing is not linear either. Right? So I tried to get something like that. I didn't quite try to calibrate it to certain decibels. I just kind of played around with the numbers depending on what the top and the bottom are. So for example, here, if I lower the resistance on both potentiometers to something quite low, you'll see that my threshold voltage for the whole VU meter goes up, but more so at the top end here. So it's like 3.2 volts. If I increase this all the way to the maximum, okay, 3.15, or the opposite, if I lower this as low as possible and increase this to the maximum, then you can see it changes these threshold values quite a bit. One thing I will say or point out is this doesn't go up to even close to 5 volts, so 3.12. And that's actually done on purpose, because our op amp, our LM358, is not a rail-to-rail op amp. It can't actually output the same voltage that comes into it. The highest it can do is about usually 1.5 volts lower than our V-in. So the sort of maximum output voltage is probably about 3.5. That being said, I did kind of want this to be a little bit higher. These values here represent what I have on the board right now, but after playing around with this, I have changed my mind, and I actually would like this to be the ability to make this a little bit higher. So I think what I'm going to do is actually remove our second resistor here. And so then I can get a little bit closer to that 3.5. And likewise here, I ended up not liking sort of what values I could get here. Like if I go very low, go 0, that's fine. But if I go to the maximum, 0.16. But I think what is better is if I add another resistor between the potentiometer and ground. And then I can get a little bit higher voltage. Anyways, something like that. So this is useful as far as like trying to get a sort of ballpark value of what your thresholds will be for your VU meter based on the signal. So like I said, a couple of modifications. I think I'm going to remove this second resistor and attach this resistor right to the first potentiometer, which is connected to the second. One thing I should mention, forgot to mention, is these 3 potentiometers. They're only connected in 2 spots, right? There is one pin not connected here, and then not connected here. So it's just one pin, and then the wiper is connected to ground. Okay, this is connected to the wiper, and then one pin is connected to the wiper of the second potentiometer. Okay, so if you're looking at this and wondering, well, where's the third connection? They aren't connected. So those are 2 modifications. I think I can put another resistor here in between this potentiometer and ground, give me a little bit more control at the lower end here, and get rid of this one here, give me a little bit more control of the threshold for the top LED. So what is this doing now? Like I said, it's not actually working like I want it. So this is a breadboard power supply. So this side I can get 5 volts here. So let me plug in my device into ground. and then here is the VCC. Okay, and then this has a power, so let's turn this on. You can see the green LED, and then this has an on-off switch here. And so now, right now you see there are 6 LEDs, but it's not really responding to sound. So there's something wrong with this part of the circuit. I've been poking around. So actually the output, this pin 7 here, let me turn this off. It is, so when I did it, there it is connected up to the top here underneath. You can kind of see this sort of silver wire here. It's not silver, but that is right underneath this ground line that I tried to run on the outside, and then realized I needed a ground from down here, so I tried to tap into this ground line. I meant to attach it not over top there, maybe a little over, but I don't know, for whatever reason, I ended up making it there. And so I think I can see that these are actually shorted together, those two, so that's not good. When I use my continuity meter on the multimeter, yeah, they are connected. So I think if I get a hot soldering iron and just kind of wipe off some of the excess solder, I think I can remove that. Or if I have to maybe put like Kapton tape in between to insulate the two, something like that. Otherwise, I think that might be it. Hopefully that's it. Actually, there's one more mistake here. This feedback diode has its cathode pointed towards the inverting input. It actually should be the other way around. So that's something else I'll have to fix. So with those two adjustments and then hopefully removing that, I'm hoping that this will work. The LED portion, it does seem to work. So like I said, I'm able to separate that part of the circuit from the microphone. And so when I do that, I was able to demonstrate to myself that, yes, in fact, the LEDs do seem to work. So like I said, this center pin here is connected to the blue. So if I connect that, and then over here I have another potentiometer. If I connect there, then if you know, potentiometers are kind of like voltage dividers themselves. So now the blue wire is connected to this and not to the microphone. I turn that on and then turn this on. Then again, so now you see that there's not just 6 LEDs. And if I turn this potentiometer with this screwdriver, you can see that if I turn it back and forth, yeah, I get different numbers of LEDs. And that's really what this should be doing, although it should be responding to sound from the microphone. But for some reason, I only get the 6, and I'm hoping it's that short circuit there of the output on this side. So that's it. So hopefully you found that interesting. It's kind of a neat project if you're trying to learn about op amps. Different configurations and as comparators and amplifiers. So I think it is a pretty neat project. Hopefully those modifications that I have in mind work, and then in the next video I will have a working model that I can demonstrate. Thanks, and I'll see you in the next video.